principle of superposition of waves, it states that when two or more waves traveling through a medium pass through a common point, each wave produces its own displacement at that point, independent of the presence of the other wave. The resultant displacement at that point is equal to the vector sum of the displacements due to the individual wave at that point. In the diagram, you can see that superposition of two wave pulses of equal amplitude and same phase moving towards each other is shown in the first diagram, and in the second diagram, superposition of two wave pulses of equal amplitude and opposite phases moving towards each other is shown. Let us study the first diagram. Suppose that two waves cross each other between t is equal to 2 seconds and t is equal to 4 seconds as shown in the diagram. Here, the two wave pulses superpose and the resultant displacement is equal to the sum of the displacements, that is shown by the full line at t is equal to 3 seconds due to the individual wave pulses which are shown by the dashed line. This is called as constructive interference. The displacement due to the wave pulses after crossing at t is equal to 5 seconds and t is equal to 6 seconds are also shown in the diagram. After crossing each other, both the wave pulses continue to maintain their individual shapes. Now let us study the second diagram. In the second diagram also, the propagation of approaching wave pulses and their successive positions after every second is represented. These wave pulses superpose at t is equal to 2 seconds and the resultant displacement, that is full line, is 0 due to individual displacements, that is dashed line. And now you can see here it is differing in the phase exactly by 180 degrees. This is called as destructive interference. Displacement due to one wave pulse is cancelled by the displacement due to the other wave pulse when they are crossing with each other. After crossing each other, both the wave pulses continue to maintain their individual shapes. Now let us apply principle of superposition in order to find out amplitude of the resultant wave produced due to superposition of two waves. Consider two waves having same frequency but different amplitudes as A1 and A2. Let these waves differ in phase by phi. The displacement of each wave as x is equal to 0 is written as y1 is equal to a1 sin omega t and y2 is equal to a2 sin of omega t plus phi. Now, according to the principle of superposition of waves, the resultant displacement at x is equal to 0 can be written as y is equal to y1 plus y2. Y is equal to a1 sin omega t plus a2 sin of omega t plus phi. In order to write down the further steps, we have to use the identity sin of a plus b is equal to sin a cos b plus cos a sin b. We can write y is equal to a1 sin omega t plus a2 sin omega t cos phi plus a2 cos omega t sin phi. In the next step, we can write a1 plus a2 cos phi in the bracket and sin omega t is taken out of common plus a2 sin phi cos omega t. Now we can write A1 plus A2 cos phi as A cos theta and A2 sin phi as A sin theta. We get above equation as y is equal to A cos theta sin omega t plus A sin theta cos omega t. We will know that this is the expansion of sine of omega t plus theta. So in the next step we can write y is equal to A sine of omega t plus theta. Equations 6.4 and 6.5 can be squared and added. After that we can get A square cos square theta plus A square sin square theta is equal to A1 plus A2 cos phi bracket square plus A2 square sin square theta. In case of left hand side, cos square theta plus sin square theta becomes 1. So we can write A square, which is equal to A1 square plus 2A1 A2 cos phi plus A2 square cos square phi plus A2 square sin square phi. In the next step, we can consider cos square phi plus sin square phi as 1, and we can write A is equal to under root A1 square plus 2 times A1 A2 cos phi plus A2 square. This equation gives us the amplitude of the resultant wave produced due to superposition of the two waves. Now we are going to consider two special cases. First case, when phi is equal to 0, that means the waves are in phase. Then the resultant amplitude can be written as A is equal to under root A1 square plus 2 times A1 A2 cos 0 plus A2 square. We know that cos 0 is 1. So in the next step we can write under root of A1 plus A2 bracket square. Then resultant amplitude becomes capital A is equal to A1 plus A2. This resultant amplitude is maximum when phi is equal to 0. If the amplitudes of the waves are equal, that means A1 is equal to A2 is equal to A, then the resultant amplitude becomes 2 times A. Second case, when phi is equal to phi, that is, the waves are out of phase, then the resultant amplitude becomes A is equal to under root A1 square plus 2 times A1 A2 cos phi plus A2 square. Cos phi is nothing but minus 1. So in the next step we can write under root A1 minus A2 bracket square. So the resultant amplitude becomes mod of A1 minus A2. Thus here resultant amplitude is minimum when phi is equal to phi. If the amplitudes of the waves are equal, that means A1 is equal to A2 is equal to A, then the resultant amplitude becomes 0. We are going to consider the relation between intensity of wave and amplitude also. When phi is equal to 0, maximum intensity is directly proportional to A maximum bracket square, that is A1 plus A2 bracket square. When phi is equal to phi, then minimum intensity is directly proportional to A minimum bracket square, which is equal to A1 minus A2 bracket square.